Hello everyone, welcome to the Learning Express YouTube channel. In this video, I have designed a presentation where I have listed down few questions related to the analog electronics and all other basic subjects and instrumentation basics. So these questions might help you people who are going to appear tomorrow for the interview at the electrical department IIT Kharagpur. So I have listed down these questions like in BJT, I have formulated or I have designed some few questions like the structure and the circuit symbol of NP and PNP transistors. So these are basic questions I have mentioned here. I am not going to read all the questions, otherwise the video length will be very large. So you can look on the concepts here. On basics terminologies are explained here in terms of whatever the writing I have provided here, and you can also search it by your own. So this is the kind of quick revision that you can do it before interview. So, so these are the few questions. This a large signal model is important. You can see it here. So this large signal model is important. In this, your collector current and base current together form as a emitter current. So between this base and emitter, there is a diode connect, or can say there is a diode formation, which is controlled by VBE voltage. So expression for IB is this, and expression for IC is this. So this is basically the large signal model. And we know the IB characteristics. One IB characteristic is between the input voltage and current, and second IB characteristic is the output voltage and the current. So input voltage here is your base to emitter voltage, and output voltage here is a collector to emitter voltage. So one characteristic is like this, and other characteristics like this. So I think all of you know this basics. And a small signal model we all know, and current relations we all know, how the IC, IB, and IE are related to each other. And after that, the reason for early effect. So reason for early effect, we know when we apply the large collector base reverse bias voltage. So when this collector to base biasing is done with a large amount, then we can say your depletion region is penetrating more toward the base region. And after one point of applying of this voltage, we will see the almost constant current. And if we want to graphical representation of early voltage, you will see graph like this. So this is like a graph. And when we extend this graph on the other side, we can see it as a early voltage. This is a V early. And this is your collector to emitter voltage. And this is your IC. So this is the early voltage. And for the saturation, you can revise your gate notes. In saturation, we define amplifier basically. That's why I mentioned a saturation region. Then the discuss the need of biasing. I have mentioned few points here. You can read it properly. Because with the biasing, with the help of biasing, we set a transistor ready for the amplification. So biasing is nothing but a proper application of collector to emitter voltage, so that we have some proper current there. So this IC versus VCE, this particular point is known as the operating point, and according to that, at particular value of VC, we apply the small signal voltage, and this small signal is amplified. So this is nothing but a DC voltage over which our small signal is superimposed for amplification. So next thing is the emitter injection efficiency and base transfer factor as two important terms. You can read it from here or you can Google it. But I have mentioned here that, so we have the emitter current. So some part of emitter current is recombined in base, which is undesired. So whatever the amount of emitter current entering into the collector is nothing but a fraction of emitter current. So basically, emitter current has two components. One is your large component, and other is a small component. So the small component is almost negligible. So fraction of emitter component or emitter current that is entering into the base. So the ratio of that current to the total emitter current is known as your emitter injection efficiency. And the fraction of emitter current that is entering into the collector region after passing from base region. So because some current is recombined in base. So that ratio is defined as the base transfer factor. So I think no need of these things to go into detail, but you can revise them like these basic terms are, and why this silicon type transistor are more often than germanium. You can see it here. And why collector is made larger than the emitter. So collector is like where we need to, because its area is large, there is a huge power dissipation in collector region because we collect many carriers there, and when these carriers are reaching toward the collector, there is a heat dissipation, and to remove this heat out of the device, we make the collector region large. Now, why emitter is always forward bias? I have mentioned here. Why collector is always reverse biased? Mentioned the point here. And yeah, two back-to-back connector diodes can we form BJT by it? I think we cannot form the BJT by it. So two back-to-back connected diode cannot be used as a BJT model. But if we make some correction here, two dependent current sources are used, then this particular model is called the ever small model. This two diodes can be used as a BJT model when two dependent current sources are also used. So this is a relation between alpha and beta, and alpha is around 1, we know, and beta is a large value. This is usually we use a 50 to 100. This is your beta. So this is the basic relation. And why common emitter configuration is popular, I have mentioned here the points. And one table I have listed down few points, and I have remember it like the VOIC, voice you can also remember, voltage gain, output impedance, input impedance, current gain, and these are the sequences. Common emitter is moderate in all the values, and after that your common collector and common base are around that. And why common collector configuration is called a voltage buffer, I have mentioned here. And what is its other name? So its other name is emitter follower. And why it is called a buffer? Because its input impedance is high. From this point, you can see its output impedance is low. So when there is a requirement of connection between some high impedance source circuit to the low impedance load circuit, in between that we use some circuit that is called the voltage buffer. So common collector can work like that. So the last question is, a transistor operate as an amplifier. How it operates as an amplifier? So I have mentioned here. So please go through these points very carefully. I am not going to read them. I have designed this content, and now you can revise it. So the next thing is MOSFET. In MOSFET, I have mentioned here few questions. Is MOSFET a symmetric device? So you can see the MOSFET is symmetric device. Basically, this is a structure you all know. So drain and source. So this is your, if you considering this source and drain, so these can be used interchangeably. This is your gate. So these two can be used as interchangeably. So I can say this your MOSFET is a symmetric device. So whatever the potential is larger, that can be treated as a drain. If it is a source, in generally mentioned like this is a drain, this is a source, and this is a gate. But yes, if potential is larger here, it will work as a drain. If the potential is larger here, it will work as a drain. So it is symmetric device. Structure and circuit symbol of the MOSFET, you all know. You will do it. Now, significance of polysilicon and insulator. So polysilicon is a material where we usually make the connections. So we can use the polysilicon. We can also use the metal here. In general, initially we use the metal like aluminum here for making the connections over the gate region. But now we replace this thing totally with the polysilicon. So this polysilicon is mainly used for the gate connections. And the source and drain are connected by the metallization. And insulator is nothing but silicon dioxide, which is between the substrate and metal. If this is a metal, there is a layer of silicon dioxide, and below that there is substrate. And below that there is substrate. You all know this MOS structure. So this is your silicon substrate. It's completely silicon substrate. And this is your insulator. There is a SiO2. And this is a metal. This is a metal or polysilicon or poly. So you can revise these things from your notes also. So operation of MOSFET. Operation of MOSFET you all know. And reason of operations. So in terms of, if I talk about the operation, then we talk about the gate voltage. When we apply the gate voltage, we form the channel. And once we form the channel, we apply the drain voltage or drain to source voltage for current flow. Drain to source voltage for current flow. This is under the operation of MOSFET. And now the regions of operation. Regions of operation we know cutoff region, saturation region, or triode region, basically called the active region in terms of BJT. So this is here triode region. And IV characteristics of MOSFET. All the equations of current we all know. IV characteristics like same as when we draw the between the VGS and ID. So it is like this. And when we draw the ID versus VDS, so it is like this. Or practically it is like this. So you know this is the VTH. This is VGS. So this is the VTH. After the channel is formed, and so this particular region is subthreshold conduction. This is subthreshold conduction. After there's a deep diode, not deep diode. It is a deep inversion region where we have a significant amount of current here. So what is the pinch-off effect? When we apply the drain voltage and we are increasing the value of drain voltage, so at one particular point, there is a formation of large value of, so there is a formation of large value of depletion region here. So if this is your source region, this is your drain region, and we are applying more and more value of the drain voltage, then there is a formation of this particular depletion region. And this particular depletion region is very small. This depletion region is very small. So at particular point, this channel is like this. So here is like very small space remained for flow of the carrier, so flow of the electrons. So this particular point, when your drain voltage is that much, so that only a few electrons are capable of flowing across it, known as a pinch-off effect, and you can search it. And this channel length modulation in BJT. This thing is channel length modulation in BJT, not in BJT, in MOS. BJT it was early effect. In BJT it was early effect. So in triode CLM exists or not? So in general we can say there is a no existence of CLM in triode region, because when VDS is large enough so that our transistor is already in saturation, and when this VDS is extending above that particular value, then CLM will occur. So CLM cannot occur in triode region. Now, they define the transconductance. So there are a few expressions for the transconductance. Basic expressions we all know that transconductance is nothing but 2ID mu n CUX WIL that we usually use, and the other expression is 2ID divided by overdrive voltage, that is VGS minus VTH, and one more expression we use. So please look into these expressions. These are important terms. What is GM and what is CLM? These all are important. What is the body effect is also important. So what is body effect? So body effect, you all know that when your body and source are not at same potential, then this body and source potential is non-zero. And if this body source potential is non-zero, usually we connect the body with the ground for NMOS and body with the VDD for PMOS. Usually we connect it. Like if it is your NMOS, then body is connected with ground. And if it is a PMOS, your body is connected with VDD or the more positive potential. If your maximum positive potential of the system is VDD, then your body is connected to VDD for PMOS. So conditions for all the regions of operations, we all know the conditions. The SVG should greater than the VTH for formation of the channel. And after that, VGS minus VTH should be less than VDS, and VGS minus VT is greater than VDS for saturation and triode regions. And please look these things for the PMOS transistor, because it might be confusing sometime. So please look at the symbol, expression, and equations. For the PMOS, there is a slight change in the equation. In general, when we write in the saturation region, IDS, it is like mu p COX for saturation, WIL divided by 2. So here we write VSG minus VSG minus VTH whole square. So this VTH is nothing but negative value, so we use its magnitude, and 1 plus lambda VSD. So please be careful. It is a VSG and VST. But for NMOS, we use VGS and here BDS. So please be aware of, or not aware, but careful of these things. Don't be confused there. Now, the small signal model, including body effect, we can draw it. And I'll also mention some video playlist that I have designed for the intuitive analysis of the basic amplifier. So the current equations, including body effects, small signal model using body effect, and MOS amplifier, small signal with intuitive analysis. So these things I have already explained in video playlist that I will mention here. So yeah, body effect is important. Please remember all the current equations, including body effect and a small signal with its intuitive analysis for the amplifier reason, including body effects, including CLM, and with or without CLM. Now, come to some common points. So yes, analog, I have left with a few points of operational amplifier. So for op amp and diodes, I have few points. Okay. So for op amp, please look into the characteristics, ideal characteristics, practical characteristics. And after that, you can look into the basic circuits like adders, subtractors, differentiators. And important thing is there in differentiator and integrator, there is a difference between some practical and ideal integrators and differentiator. We use resistor. In general, when we use only capacitor for the integrator, and after that we connect some resistance. I think you people can connect it, whatever I am talking about. So please look at this particular point, practical integrator and practical differentiator very carefully. And after the precision diode and other applications of this op-amp circuits, half-wave rectifier waveforms you can see. And for diodes, I have mentioned it for the diodes, clipper and clamper circuits, you can revise it from your gate notes. And after that, inverting, non-inverting configurations. And for diodes, you can remember the different kind of modelings. And for analog circuits, when two diodes are connected in parallel or two diodes are connected in series, so questions will be very basic. They will not like a huge circuits will be asked here, but simple two diodes are connected in parallel with different cut-in voltage, and two diodes are connected in series with different cut-in voltage. And if you're applying some external potential there, what will be the response? So such questions can be asked. And I mentioned here for the op-amp, you revise these basics circuits. Now come to the common points. In mathematics, usually in interviews, in mathematics, they ask the matrix algebra. So revise it from your notes. Now signal system, I have mentioned strictly in a previous video, I mentioned some generalized concepts, but now I mentioned few most asked things like energy and power signals is an important thing. And in Laplace transform, some elementary signal like unit step, ramp, parabolic, sinusoidal, and exponential. So these are most usual signals, or can say most elementary signals. These are used at many places in different circuits. So the Laplace transform of these signals should be clear. And the next thing is a Fourier transform of some basic signals. And after that, the Fourier series coefficients with the different conditional symmetries. I have mentioned the half-wave symmetry, quarter-wave symmetry. So these symmetries are mentioned here. So please look into these symmetry concept for Fourier series. And according to these symmetries, how your Fourier series coefficients means an, bn, and the average value a naught, how these changes. So please look at these things very carefully. And next thing is control system. So here I mentioned negative feedback. It is very important. You can consider it as very important for the control system, and how to identify the feedback. It is very important. Suppose this is the circuit, and you have input here, and you are giving it feedback here. So this is simply the feed forward path, or this is a forward path. So this is some adder kind of thing. If you are applying here, so if you don't know what kind of feedback is, this is your input and this is your output. This is your output. So if you are increasing your input and you're getting output to be increased, and with this increased value of output, if you are further getting increment in output, means it is a positive feedback. And if you're increasing the input and you're getting output is decreasing, and with the decreasing value of this feedback, because the output is nothing but a feedback, and if the decreasing value of feedback is again causing increase in the output, and this increment in output as a feedback is causing again decrement in output. So this kind of thing is like a negative feedback. So in negative feedback, circuit cannot be destroyed. But in positive feedback, this is a process of accumulation. So there is a chances of destroying of the circuits. So usually positive feedback circuit is like eh, after one point you will enter into the saturation, because with the increase in with the increment in input you are getting increment in output, and that increment is fed at the feedback, so again you are getting increment in output. So this is the accumulative process. So this next thing is, so this is the identification of feedback. Now next thing is where positive feedback is used. So you can see it in the oscillators, wave shaping circuits like Smith trigger circuit we used. So such question can be asked where we use the positive feedback. Now, phase margin, gain margin values for stability. Usually know that these should be positive values, phase margin and gain margin. You should clear with the meaning, and also what should be their sign and values for stability. Pole location for the stability. What the meaning of pole when it goes on right and it goes on the left side of the plane, and idea of all the plots, Bode plot, Nyquist plot, and root locus, and all type of system responses for different values of zeta. So it is also important thing. So for what value it is underdamped, overdamped. So these are basic questions that you should always clear with. In network analysis, maximum power transfer theorem. I have mentioned this theorem in the first, so it is very important. Maximum power transfer theorem. And in transient analysis, you should have some intuitive idea that the value of capacitance, where we know that at t equal to 0 and t equal to infinity and t equal to minus infinity, we'll know the value of capacitance in the circuit. And on the basis of that capacitance value, capacitance voltage value, we can find our output voltage. So usually this analysis should be done in RC circuits. So please go with the small or basic RC circuits so that you can have the idea while they will ask the questions. So now the time constant. So time constant is very important. You should have the idea of charging time constant, discharging time constant, and up to what charging percentage we define the time constant, up to what discharging percentage we define the discharging time constant. So we must clear with this thing. We must have clear idea about these. Now the next thing is Thevenin voltage and resistance calculation. This is also important. So we should be clear with these steps, how to calculate the Thevenin voltage, how to calculate the Thevenin resistance, and what should be the criteria, or how we apply and why we make the source zero source, and how to calculate it by taking some test source here. So please be careful of all these things. And now the output voltage equation for the circuit, mainly RC I mentioned here, when your source is applied or the AC source is applied. So this thing basically we see, suppose this is your RC circuit, and here you are taking the output V out, and here you are applying the V input, and this input is nothing but a sinusoidal, and according to that you will get the output. So this in between circuit is nothing but you have some transfer function for it. On the basis of the transfer function, when we replace its frequency with this the input signal frequency, you will get some phase and magnitude, and according to that phase and magnitude we have this output V out. So I think these things are usually asking gate, so you people should have the idea. So this is some kind of AC analysis where we apply the input or some AC input across some circuit, and its transfer function is used for its magnitude and phase plot of the output. Now, now come to the instruments and basics. It is very important here. So I have defined here what is actuator. I have defined, and usually we control the device using the actuator. So suppose the hydraulic, pneumatic thing, and electrical or magnetic devices are there. So we use the control signal here out of these, and actuator is used in between, and after that we connect the mechanical motion. So the component of machine, basically the actuator is a component of machine responsible for moving or controlling it. So I think you can also revise this thing from these whatever the notes I am providing, and also you can search these things over the Google. I think don't have this much time, but you can look these things like here, what the actuator is. And next thing I mentioned, sensors versus transducers. I have defined here, so please go through these definitions. And basically, the sensor is a physical sensor senses the physical quantity and convert into some output, like electrical output or any other kind of output, which can be modeled or handled further in the circuit. And transducer is something which is nothing but a combination of sensors and signal condition. So sensor is taking physical quantity and converting into some electrical quantity or some other quantity, and this electrical quantity is handled or can say modified by signal conditioning circuit, and which further is used or further is converted to the electrical quantity only, but with can say large value. If we are getting small value of voltage at the output of sensor, we can amplify it, we can smooth down this waveform and can use it after that. So basically, it is nothing but transforming of the energy from one form to another for transduction. So please go through these definitions. And after that, one important thing I have mentioned here, the temperature sensor. In temperature sensor, we basically use these three sensors: thermistor, thermocouple, and RTD. And I have listed down the basic differences between these all three, and also I have mentioned the definitions of these. So what the thermistor is, and thermistor, in thermistor basically there is a variable resistance, and this resistance is controlled by the temperature. If temperature is changing, the resistance will change. So on the basis of this, we can have the NTC and PTC. NTC, negative temperature coefficient thermistor, and PTC means positive temperature coefficient circuit, can say thermistor. So if your temperature is increasing and resistance is decreasing, means a negative temperature coefficient thermistor. And if your temperature is increasing, your resistance is increasing, means positive temperature coefficient thermistor. So thermocouple are also devices where we connect two dissimilar materials. So when we connect two dissimilar metals, this is the wire 1, wire B, wire A and B. So these two are dissimilar. And this is your hot junction and this is your cold junction. So due to the temperature difference and two dissimilar materials, there is a formation of voltage difference between these. And this voltage difference can be measured by this. This is a millivolt order and whatever it. So this is mainly the thermocouple. And after that, RTD. So this is the RTD. So I have mentioned here that an electrical current is passed through the resistance. And on the basis of that electric resistance, we measure the resistance of the current being passed through it. So I have mentioned here, so this particular thing is mentioned for the RTD. And this is for thermocouple. This is for thermocouple. Yeah, this is for thermocouple. This is for thermistor. So please look these all three sensors very carefully. And apart from it, I have mentioned some other important sensors here, like accelerometer, thermometer, proximity sensor, ultrasonic sensor, level sensor, motion sensor, capacitive sensor, photoelectric sensor, Hall effect sensor, and IR sensors. So after that, you can also get some more sensors. Please look at the definition and simple, basic, and working principle of them. If you time permits you, simply go through the basic definitions. And I have mentioned here. Okay, so important links for sensors. So whatever I have mentioned in terms of the various sensors, I will mention the links, two links where I visited and researched this content. So please go through these links. I will mention in the description. Provide some information related to your interview question. So I am again recap it. So okay. So initially I mentioned the BJT and basic questions of BJT. Please go through it very carefully. And after that, some basic questions of MOSFET. And for amplifier, I will list down my video playlist here. And then some common points: mathematics, signal system, control system, network analysis, and then instrumental basics. So this thing is mainly designed for IIE branch and people who are appearing for the interview. I okay. One thing that is important, I forgot to mention here. The important thing is about a panel. So one important thing is here about your panel. So people who got call from suppose two different specializations of double E or three different specializations of double E. So three professors from all these specializations will be there in your panel. If you got the call from IIE, then one professor from the IIE. If you also got call from control engineering, then second professor will be from control. And if you also have the call from SPML, then professor from the SPML. So in your panel, there will be three professors. So it will be like this. So I got this information, this is the internal information, but I am mentioning here. So if you got the call from two specialization of double department, three specializations of double department, then accordingly two, three professors will be there. So look at these things carefully. So I think I tried to explain the things, and this is enough for this interview session. So thank you.